now going to do a full hypothesis test for means. I'm going to warn you, it's a lot. I normally, when I go over this in class, give about 4 examples like this, then have you try a couple. It's something that definitely takes a while to get down. The key thing you want to be focused on is understanding each of these 5 steps that I've listed at the top of the paper and how to complete each of them. The first one we already did on the front side of the paper. It's setting up the null and alternative hypothesis. So when I look at the full question number 11, it says a light bulb manufacturer wants to make sure their light bulbs last more than 10 years as they claim on their packaging. Right from that sentence, I should be able to pull out what they're trying to prove, the alternative hypothesis. In this case, the alternative hypothesis is that the mean amount of time that the light bulbs last is greater than 10 years. That must mean that the null we're trying to disprove is that the mean amount of time that they last is equal to 10 years. They then give us the information that they take a sample of 60 light bulbs. The sample size, or how many light bulbs are involved, is going to be our n. So in this case, n equals 60. And find that they lasted 10.8 years on average. The average from a sample is x bar. If the standard deviation is known to be 2 years, in this case, standard deviation is a population value because it's known about the population. Is there sufficient evidence to say the mean time until a light bulb burns out is more than 10 years at 95% confidence? So I'm just going to write down that our confidence level is 0.95. If I can pull this information out, that's really what I need to move on and find number 2, the test statistic. The test statistic, in this case for a mean, is going to be a z-score. Specifically, the formula is going to be z equals x bar, the mean that we got from the sample, minus mu, the mean under the null and alternative hypothesis, divided by sigma or s, standard deviation that was given to us. So basically our goal here is to say, what's the probability, if this really was the mean 10, that we would get this x bar from our sample? And really this sigma is sigma sub x bar, or in other words, I should be dividing it by the root of n in this case. Sorry that I forgot that initially. So this was step 1, setting up the null and alternative. Step 2 is calculating this specific z-score. I put in the sample value 10.8 that we got as the mean amount of time that the light bulbs last, minus 10, the value under the null hypothesis, divided by the given sigma, 2, over the root of n, in this case the 60 light bulbs that we tested. So my next step here is to go to my calculator and figure out what this test statistic is. Parentheses 10.8 minus 10 n parentheses divided by parentheses 2 divided by the root of 60 n parentheses. This tells me that I get a z-score of 3.098. I know that whenever I have a z-score, I need to be using a table which only goes to 2 decimals. So here, I'm going to drop this 8. Since it's bigger than a 5, I round up. Since this is a 9, it really rounds up again. So this final answer is 3.10. We've now calculated the test statistic, so we're done with part 2. Part 3 asks us to find a p-value of the test. There's 2 parts to finding this p-value. The first thing is we're going to look up the table value associated with 3.10. So on my table, I make sure I'm on the positive side. I go down the left side to 3.1. In the first column marked O, I get a p-value of p equals 0.9990. I'm not done with step 3 yet, because what I now need to do is put this in context of the alternative hypothesis. The alternative hypothesis has a greater than here. So we're looking for the probability we get something more than what we got in the sample. In other words, if we think about it on a normal curve with 10 being where we're centered. centered at the mean under the null hypothesis. And we now get a sample value of 10.8. We want to figure out what's the probability we got this sample value or something greater than it. So we want to find this shaded area. When we ran our z-score, we said that this was the z-score 3.10 that's associated with this spot. So to find the probability that we get to the right of that, we're going to need to take table value, which tells us everything to the left, and do 1 minus that. So if I do 1 minus 0.9990, I get 0.0010. This is the correct p-value for the test. So here we've completed number 3. Understand that there's 3 different symbols that can go here in the alternative. Each one has a different process. For greater than, after we looked up the probability, we had to do 1 minus. For less than, we could just use the probability that we looked up in the table. We're going to see that when we have not equal to, that's the most difficult version. Not equal to has to consider both tails. So basically I have to see whether I have a negative or positive z-score, find the probability using that method for either greater than or less than, and then double the probability to count for the other tail. You're going to see that in a problem coming up, but for now all you really need to see is, since it's a greater than test, we were worried about this side of the curve, we had to do 1 minus the p-value. So we now have 0.0010 as the probability of the test. We need to compare this to an alpha, or a confidence level that we were given. In the problem, it said 95% confidence. That percent confidence implies that we're willing to be wrong 5% of the time. If we're 95% confident, then we're 5% not confident. Another way of seeing this is if you take this confidence level and you do 1 minus the confidence level, 0.95, that gives you 0.05, or alpha. Alpha is really a way of saying the chance of making a type 1 error. So the chance that we randomly ended up in here when really the mean was actually 10 is our chance that we made that error in the actual problem. Here we found that probability was 0.0010. We want to compare it to what our threshold was, 0.05, that we were willing to work with. So the question is, which is greater? The test probability, or our alpha, the threshold for how many errors we're willing to make. In this case, alpha is greater. When alpha is greater than test probability, our answer is reject the null. To sum up what happened here, if it really was the case that these light bulbs lasted 10 years, the chances of us randomly selecting 60 light bulbs that lasted 10.8 years on average would have been about 0.1%. We said if it's less than 5%, because we want to be 95% confident, that's going to give us enough information to say, no, this must have been wrong. The alternative is true. So here it was significantly less than alpha. It was 0.1%. That's why we say we must have been wrong. 10 is not the mean. These light bulbs on average last more than 10 years. We've now proven it statistically using this sample.